Assalamualaikum warahmatullahi wabarakatuh and good afternoon. So today we're going to discuss on chapter 3, Amplitude Modulation and Demodulation. So what is modulation? So basically the purpose of communication system is to transmit information signal, which is the baseband signal, through a communication channel. The term baseband is used to designate the band of frequency representing the original signal as delivered by the input transducer. For example, our voice, if we speak into a microphone, is a baseband signal. So the frequency is the range of our voice, which is from 0 to 3 kilohertz. If you look at this picture, this is a baseband signal. If you say hello, so the frequency is very low, and we can only transmit or send this signal just few meters away. The louder you speak, the further it can go. However, if you want to transmit this baseband signal for few hundred kilometers, so you have to do the modulation. So the modulation basically is a combination of a baseband signal with another frequency signal. We call it carrier signal, which has a higher frequency than the baseband signal, and it envelops the baseband signal so that it can be transmitted further away, few hundred kilometers, for example. So here we're going to look at the amplitude modulation. There are other modulation, for example, frequency modulation, phase shifting modulation, but here we're going to focus on the amplitude modulation. So amplitude modulation is the process of changing the amplitude of the carrier frequency in proportion with the instantaneous value of the modulation signal. So basically it used in two-way mobile radio communication. For example, citizen band, CB radio, amateur radio, and so an modulator are non-linear device, which is 2 input and 1 output. So the 2 input is the modulating signal or the baseband signal, and another one is the carrier signal, and the output is the combination of both two signal. We call it amplitude modulation signal. Modulating signal or the baseband signal, we call it VMT, may contain a single frequency or multiple frequencies such as human voice. So there are several types of amplitude modulation. The common one is AM DSB FC, amplitude modulation double sideband full carrier, or simply say AM. Other type of amplitude modulation are DSB SC, suppressed carrier, and DSB RC, reduced carrier. Another one is SSB, which is the single sideband modulation. So this is the general view of the how modulation works. So we have a modulator here, a circuit, and the input is the information, which is the modulating signal or the baseband signal, and another one is the carrier signal, VC. So modulating signal is VM, VC is carrier signal, and the output is the modulation signal, amplitude AM signal. So V2 is equal to V1 sine 2FC. The FC is the frequency of the carrier signal. So if you look at this slide, there are 3 types of signal. So at the bottom here is the AM signal, which has been modulated. On top here is the carrier signal, and the middle here is the modulating signal. So the modulating signal is basically the baseband signal, which is our voice. And here On top is the carrier signal, which will be combined with the modulating signal to create a AM signal. So if you look at here, basically the red signal here, wave here, is the modulating signal, while inside of this is the carrier signal. So if you compare between both carrier and modulating signal, the carrier signal has a higher frequency compared to the modulating signal, because for one cycle of modulating signal is very wide compared to the one cycle of the carrier signal. From this time frame, one cycle time frame, we can calculate the frequency. So the equation is F equal to 1 over T. F equal to 1 over T. So from here, if you calculate 1 over 0.01 second, you can get frequency. And if you compare both of these signal, the carrier signal has a higher frequency compared to the modulating signal. So this is the mathematical representation of the AM modulation, amplitude modulation. So let's say the carrier signal VCT and the modulating signal VMT is like this. Take this equation 2.1 and 2.2. So VC equal to VC sine 2 pi FCT and VM is equal to VM sine 2 pi FMT. So F is the frequency, T is the time, and V is the voltage of the signal. From this graph here, or signal here, we know that VC for carrier signal is 10 volt and VM for modulating signal is 5 volt. So modulating signal use the peak value of carrier as a reference point. So modulating signal value add to or subtract from the peak value of the carrier. So because of the voltage of the modulating signal, VM is referring to the peak of the carrier signal, VC. So that's why this equation 2.3 is represented. So V envelope is equal to VC plus VMT. So V envelope is equal to VC plus VM sine 2 pi FMT. So the signal is known as the envelope of the modulated wave. So V envelope T. The instantaneous value of modulated wave is VAM equal to VC plus VM sine 2 pi FMT times sine 2 pi FCT. So from this equation, we can conclude that the last equation is V amplitude modulation is VC sine 2 pi FCT plus VM over 2 cos 2 pi FC minus FMT minus VM over 2 cos 2 pi FC plus FMT. So the first equation is the carrier signal. The second equation, VM over 2 cos 2 pi FC minus FMT, is the lower sideband, and the last is the upper sideband. So how we want to represent that equation? So we have carrier signal, lower sideband and upper sideband. So we can use spectrum frequency spectrum to represent that equation. For example, if you look at this frequency spectrum, we have an FC at the middle, and on the left and right is the lower sideband and upper sideband. So the x-axis is the frequency, while the y-axis is the amplitude, which is the voltage. From this frequency spectrum, we can also determine the bandwidth. So how we want to calculate the bandwidth? So the bandwidth is equal to 2 FM, which is the range between the lower sideband to the upper sideband, and FM is the bandwidth from FC, the middle here, to the FC plus FM or FC minus FM. So other than that, you also need to know the modulation index. The demodulation index M is merely defined as a parameter which determines the amount of modulation. So modulation index M is equal to Vm over Vc. So in a percentage, M is equal to Vm over Vc times 100%. So for the proper AM to occur, this condition need to be achieved. So Vm should be less or equal to Vc. So by this definition, we could distinguish three different type of amplitude modulation. So we're going to discuss on under modulation, where M is less than 1, ideal AM for M equal to 1, and over modulated AM for M above 1. So let's look into this condition. So the first condition is M is less than 1, and we know that Vm should be less than Vc. So M less than 1 is under modulation. So signal strength obtained at the receiver is not exactly the same as the signal strength at the transmitter. No distortion to the signal, just reduce signal strength. So we get a normal amplitude modulation signal at the receiver. So no problem. So no problem to receive the signal. So the transmitter produce a good amplitude modulation signal. How about M equal to 1, which is the ideal modulation, where Vm is equal to Vc. So it will produce greatest output at the receiver without distortion. Maximum info signal amplitude is transmitted. However, it is hard to achieve, especially when the modulating signal amplitude varies randomly over wide range. For example, our voice, the amplitude is not fixed. So it's hard to get 100% modulation. Usually we will get M will be less than 1. So how about M modulation index higher than 1, which is over modulation? So in this case, Vm is larger than Vc. So this will cause distortion and it produce negative peak. Negative peak have been clipped off. So the original shape of the signal is destroyed. So what's the meaning of negative peak? So here, so the upper band is going to the negative side, and the original shape of the signal is destroyed. The modulation index can be calculated directly from the AM signal. For example, in this picture here, in this figure here, we have a AM signal or wave. So to get the modulation index, we can use the equation Vm over Vc. So from this figure, how we can get the Vm and also the Vc? We can use this equation. Vm is equal to Vmax minus Vmin over 2, and Vc is equal to Vmax plus Vmin over 2. So to get Vmax, we just need to know the the peak of the AM signal, which is here, here, and here. So from this example, Vmax is around 13 volts here. We can say that Vmax is around here 13. So this is Vmax. However, Vmin is over here. So Vmin is the minimum voltage of the signal, which is over here, over here. So in this example, we can say that Vmin is equal to 2 volts. So we have Vmax, which is over here or over here, and Vmin. So using this equation, we can get Vmax and Vm and Vc, voltage of the modulating signal and voltage of the carrier signal. We can also determine the modulating index if they give Vmax peak to peaks or Vmin peak to peaks. So we use this equation. So modulating index is equal to Vmax minus Vmin over Vmax plus Vmin, or Vmax peak to peak minus Vmin peak to peak over Vmax peak to peak plus Vmin peak to peak. So it depends on how you interpret the figure or the AM signal. Okay, let's look at this example. A carrier signal with a peak voltage of 2 volt is amplitude modulated with a 10 kHz sine wave. The modulation voltage has an effective value of 750 millivolts. Compute the following: the percentage of percent modulation M and the instantaneous voltage of the positive and negative envelope when the 10 kHz sine wave has completed 68 microseconds of its cycle, and lastly illustrate the resulting amplitude modulation waveform. So let's look into the question A, the percentage of the modulation index M. First, let's look into the question. So they give Vc is equal to 2 volt and Vm equal to 0.75 volts. So from here we know we can use the equation M is equal to Vm over Vc times 100 to get the percentage. So M is equal to Vm over I cannot erase it. Vc times 100, so you can get the answer is 37.5 volts. Sorry, not volt, percent, because it's in the percent. So this is A. And then B. So they need we need to find the V envelope. So V envelope is equal to Vc plus Vm sine 2 pi Fc t. So FC, they already given it is the 10 kilohertz, and T is the 68 microsecond. So VC and VM, we already know it, 2 volt and 0.75 volt. So it should be equal to VC is 2 plus 0.75 sine 2 pi. F is 10 kilo and T is 68 micro. So from here you will get, I've calculated it is 1.32 volt. So this is the positive envelope. So the negative envelope should be minus 1. Sorry,